Hello, so this video will cover oxidation states, which is on page 22 of your notes. Now, an element is said to be in a particular oxidation state when it has a specific oxidation number. And I'm going to show you how to work out oxidation numbers for each element. There's rules for determining it, okay? And these rules don't change. All uncombined elements are given an oxidation number of 0. So if something exists just as the element itself, not in a compound, then it has an oxidation number of 0. For ions that contain a single atom, then the oxidation number is the same as the charge on the ion. So, for example, if you had a magnesium 2+ ion, the oxidation number would be +2. If you had a sodium ion, the charge is a single positive, so the oxidation number would be +1. An aluminium ion, Al3+, would have an oxidation number of +3. For the halogens, so for a fluoride ion, a chloride ion, they will have an oxidation number of -1 because they have a single negative charge. Notice that the charge is written 2+, so for example, in a magnesium ion, it's Mg2+, but for an oxidation number, it's just +2. Now for oxygen, 99% of the time, the oxidation number of oxygen will be -2, which is the same as the charge on an oxide ion, so it's easy to remember. The only exception to that is hydrogen peroxide, where oxygen actually has an oxidation number of -1, but you're unlikely to come across this in the exam question. For the majority of exam questions, in fact almost all of them, you will be using oxygen having a oxidation number of -2. For hydrogen, again, nearly all of its compounds, hydrogen has an oxidation number of +1. Again, the same as the charge on a hydrogen ion, a single positive. The only exception to that is if you've got a metal hydride. So this is where you have a compound containing a metal and hydrogen alone. For example, sodium hydride, which has the formula NaH. In this compound, the sodium has an oxidation number of +1, and the hydrogen actually has a negative charge of -1, so the oxidation number is -1. The only example where you're likely to come up with this would be in a problem-solving style question. For the most of the time, remember that hydrogen has an oxidation number of +1. Now, if you have a molecule and a neutral compound, the overall charge on that molecule or neutral compound is 0. It's a neutral substance. And so therefore, if you add up the oxidation numbers of all of the elements in there, they should equal 0. And you can use this information to find out the oxidation number of a particular element in a molecule. If you know that they all add up to 0, and you know, for example, some of the other elements in it, you can work out one of them. Excuse me. If you have a polyatomic ion, for example, a sulfate ion or a permanganate ion, the sum of all the oxidation numbers is equal to the overall charge on the ion. So for example, the sulfate ion has an overall charge of 2-. So if you add up all of your oxidation numbers of the atoms or ions that are in the sulfate ion, then they will equal 2- or -2. If we have a look at this worked example, so determine the oxidation number of the sulfur in sulfuric acid. So the elements that we have in sulfuric acid, we've got hydrogen, we've got 2 of them, we've got 1 sulfur, which is what we have to find out the oxidation number, and we've got 4 oxygens. Now this overall, sulfuric acid, H2SO4, is a neutral molecule. Okay, so overall, all of the oxidation numbers for the hydrogen, the sulfur, and the oxygen will all add up to 0. We know that hydrogen has an oxidation number of +1. There are 2 of them, so together there's 2 lots of +1 oxidation numbers for hydrogen. We're trying to find out the sulfur. If we have a look at the oxygen has an oxidation number of -2, and there are 4 of them. So we have 4 lots of -2. So our 2 lots of +1 from our hydrogen, plus our sulfur, which we're trying to find out, plus our 4 lots of -2 from our 4 oxygens must add up to 0. Rearranging that to find out what sulfur is, we find that it's 8 minus 2, and it gives us an oxidation state of sulfur of +6. Okay, you will find oxidation states up to +7. Okay, don't worry about them. That doesn't mean that the sulfur ion has a charge of +6. It's more complicated than that. You just need to be able to work out the oxidation state, or oxidation number, sorry. So you'll do the same things for these examples here. To find the manganese in manganese fluoride, you know what fluoride is because it's a single ion, and there are 2 of them, so you can use that to find out what the manganese was. Overall, this MnF2 is neutral, so your 2 oxidation numbers should add up to 0. You can work it out for sulfur. Again, these are neutral molecules. For D, the carbonate ion, this time your oxidation numbers of the carbon and the 3 oxygens will add up to -2 because the charge on the ion is -2. And then that will be similar for F, G, and H. They will all add up to the charge that's on the ion. So have a go at those. Remember that in oxidation numbers, the sign, so plus or minus, is written first of all, which is different from the charge. Okay, now as we met previously, we said the transition metal can have different valencies because they can lose the 4s electrons, and they can also lose some or all of the 3d electrons. So we say that transition metal can have different oxidation states in its compounds. The common oxidation states are given in the diagram. So you can see for scandium, it only has 1, and that's a +3, so it loses 3 electrons, so that it has no 4s and no 3d electrons. Zinc, as you may remember from National 5, has a single valency of +2. Okay, so it only has 2, so it has no full 3d subshell. Titanium has, most common one is +4, but it also can form +3 and +2 oxidation states. Vanadium, you can see, has 4. The ones in brackets are less common. If you look at manganese, it can have an oxidation state all the way up to +7. Iron, you may remember you can get Fe2+ ions and Fe3+ ions. They're both there. +6, a lot less common. Copper, +2 is the more common, however +1 is also stable. So the oxidation states that are higher than +4, you see them, and you'll see the manganese ones quite often, but you never see them in simple ions, so you won't see just a manganese chloride or manganese oxide with that. It will be in the complex ions, things like permanganates. And these different oxidation states have different stabilities. They can also have different colors. Okay, if you watch the video, Oxidation States of Vanadium, you will see the different colors of these 4 oxidation states. You need to calculate the oxidation state that vanadium is in for each of those compounds in just the same way. For example, for VO2+, your oxidation state of vanadium plus 2 lots of oxygen will equal +1. So we can use this to relate to oxidation and reduction. Now, if you change the oxidation state, then you're changing the oxidation number of an element. And this involves the loss or gain of electrons, just as we saw in National 5 chemistry. For example, here we've got iron 2 ions changing into iron 3 ions by losing an electron. The oxidation state of the Fe2+ ion is +2, and the oxidation state of the Fe3+ ion is +3. So we've increased the oxidation number. And as you know from National 5, this is an example of oxidation. So the Fe2+ ions are oxidized, and that's shown by an increase in oxidation number. If we have a look at copper here, we've got copper 2+ ions, which have an oxidation number of +2, gaining electrons to form copper metal. Now that's a single, uncombined element, so that's just got an oxidation number of 0. So this is a gain of electrons. So as we remember from National 5, that is reduction. And we've got a decrease in oxidation number. So we can say that oxidation is an increase in oxidation number, and reduction is a decrease in oxidation number. The next part for you to do is to determine whether the conversion of the vanadate ion, VO3- into vanadium 3+ ions is an example of oxidation or reduction. So to work this out, you would calculate the oxidation number of vanadium in the vanadate ion and the oxidation number of the vanadium in the V3+ ion. And then if your oxidation number increases, then it will be oxidation. If your oxidation number decreases, then it's reduction. If you have metals in high oxidation states, these are often oxidizing agents. If they're already in a high oxidation state, then they themselves are likely to be reduced. Okay, and remember, an oxidizing agent oxidizes something else, it itself is reduced. Metals in low oxidation states are often reducing agents. So they will donate their electrons to something else and themselves be oxidized. So you can now attempt questions 42 to 50 and the check test on oxidation states. If you have any questions, please just ask. Thank you.